So we started second semester off with stoichiometry. First, let's run down the main ideas and we can do some examples of each.
Wait, where are we?
We are in room A247.
I meant like what assignment are we on?
We're on blank sheet of paper.
Note May 25th, 2021.
Thanks. You're very helpful.
So the first thing with stoichiometry, of course, right? Moles, we taught you how to find moles, right? By now, that's not something we really need to go over. Percent composition, we did empirical formulas, which we will do example of. Empirical formulas. That was also in tandem with something called molecular formulas. And then we taught you guys how to use mole ratios, like in balanced equation, which we have constantly used since then. So we're not going to spend too much time with that. And then, of course, limiting reactant problems and percent yield problems. So, remember real quick, percent composition, right? It's literally the mass of some component over the total mass times 100%.
Wait, I'm confused. What is the X on top? I need to be blank there.
It's just a variable.
So it's just like a mass number one times X.
Mass of X over total mass.
Oh.
You can move to the front in case if it's had a hard time seeing that. All right. So that's kind of self-explanatory. I don't think we really need examples. I think probably what we should do is some empirical and molecular formulas, right? So with an empirical molecular formula, what you need to do is first convert the mass to moles, right? Because in this kind of problem, you are going to be given masses to start with. So convert mass to moles. And then second, you're going to divide all moles by the smallest number of moles. And that's going to give you ratios. These ratios may not necessarily be integers, right? They might be fractions, in which case you need to resolve those fractions by multiplying them all by some common number, right? So for example, let's say that we had, something like 0.0222 moles of carbon, 0.044 moles of hydrogen, and 0.033 moles of oxygen. Okay, so you've taken the mass, you converted in moles. Here we have moles. Now let's divide them all by whatever is the lowest number, which is going to be 0.022 clearly, right? 0.022, 0.022, 0.022. Yes, extra 2, sure. All right, so 1 carbon, 2 H's, and 3 halves, or 1.5 moles of oxygen. So that 1.5, you cannot just round that. It is significant that it is in between 1 and 2. So you should recognize that as 3 halves, in which case when you have something like that where you have an easily deducible fraction, multiply everything that will resolve that. In this case, multiplying everything by 2, and that will give you C2H4O3 as the empirical formula. I'm not saying that you always have to multiply. I'm just saying be prepared to multiply if you do see some kind of pattern like this. right? So quarters, thirds, and halves are the most common. When I say quarters, I mean like you could have like 1.25, right? What would you do if you saw 1.25? Multiply everything by 4, right? What if you saw something like 1.33 repeating? Multiply everything by 3, right? Okay. All right.
I'm forgetting if carbon, hydrogen, or oxygen had charges, would that affect anything in this or no?
So in the empirical formulas, you're not worried about charges because you know that these are all bonded already. You're just trying to figure out their numerical relationship. The charges are not, they don't come into play on a problem like this. Sorry, Hilden, what was your question?
If it was like 1.9, would you round that to 2?
Yeah, yeah. Quarters, thirds, and halves. So 0.33, 0.666, 0.25, 0.5, 0.75. Okay. All right, so if you see that, or once you get the empirical formula, oftentimes you're going to have to find the molecular formula. So the molecular formula is the actual formula, whereas the empirical formula is simplified. Right? So empirical formula gives you the simplest ratio, but the empirical formula is not necessarily what the real formula is. So the molecular formula, the way that we find that is we take the molar mass of the actual divided by the molar mass of the empirical, and it gives you some integer, right? So then all you have to do is multiply the empirical formula by x, and that equals the molecular formula. So for example, let me just add this real quick and then we'll do it. Okay. Let's say that the molar mass is 228 grams per mole. And remember how our empirical formula was C2H4O3? The empirical formula, molar mass, when we add that up, is 76. So if we want to know what the real formula is, we got to take the ratio of those two molar masses. And that gives us an integer of 3. So what that means then is C2H4O3 times 3 gives us the real molecular formula, which is going to be C6H12O9. Okay. The molecular formula is a multiple of the empirical formula. So you guys can go back and you can look at any of the other worksheets and homeworks from on this topic. There was plenty of problems like this. They're not technically very difficult, you know, it's just a matter of remembering what to do. All right. So, the other thing we should probably go over from stoichiometry, maybe is a limiting reactant problem. So in any limiting reactant problem, and it's a stoichiometry problem, so you need to start with a balanced equation. So let's say that we have C2H5OH reacting with oxygen Now this is a hydrocarbon, so this is a combustion reaction. Combustion reactions always produce the same products, that's CO2 and H2O. Classifying reaction types was first semester. Yeah. All right, so let's balance this. I got 2 carbons. Always start with carbon. I have 6 hydrogens on the left, so a 3 here will give me 6 hydrogens on the right. Oxygens, I have 7 oxygens on the right. If I put a 3 here, that gives me 6 plus 1, so that is 7 on the left, and now I am balanced. Okay, so I'm burning ethanol. Yeah, don't forget, this guy hides in here, right? In alcohols, there's an O hiding in there. It's ethanol from corn. All right, so let's say that we have 35 grams of ethanol and 25 grams of oxygen ready to react. The goal is to figure out the limiting reactant, and I'm focusing on, I want to know how much carbon dioxide yield there will be. Because carbon dioxide is accumulating, we want to reduce emissions. So let's figure out how much we're going to get from this. How do I start this, guys? Moles, yep. So, ethanol.
I think I've asked this before, but is it okay if I just look at a little shortcut? Because finding moles, if I were to like divide the grams by the molar mass, I get the same answer.
That is finding moles.
Or,
What is your question?
I guess I don't have a question. Sorry.
Okay. So, we're at 46.08 grams per mole. 32 grams per mole. All right, so I've got moles of both now. Now, specifically, this is moles of ethanol here, and this is moles of O2. A common mistake that people make is they stop, they look at these numbers and say, oh, I see the lower one. That means that ethanol must be the limiting reactant, but that is incorrect. Someone tell me why. I did not convert to the desired product. I don't have this in terms of the product. You always must, in a limiting reactant problem, you must always solve both of these and get them into like terms. Like terms means the solve for the product that is in question. So the mole ratio then from the periodic table, or from the balance equation, 2 moles of CO2 for every 1 mole of ethanol. Right, so here's the ethanol, right? The 1, the coefficient of 1. And here's the... So, 1.52 moles of CO2 according to the first reactant, but we are not done. So I need to do the same thing for the units of oxygen. There's 2 moles of CO2 for every 3 moles of O2. So I am taking 0.781 and multiplying it by 2/3. 0.521 moles of CO2. So now I have 2 values. Of course, they are very different, and you can only make as much product as you have limited the reactants. So we are going to go with the lowest one. We call this the theoretical yield. And the limiting reactant is oxygen because the limiting reactant is what produces the smaller amount of product.
The limiting reactant is the smaller one, right?
The limiting reactant is the reactant that caused the smaller amount of product.
Got it.
So here's another mistake. People will often say the limiting reactant is 0.521 moles of CO2. What is wrong with that statement?
It's a product.
Because CO2 is a product, right? CO2 is not a reactant. The reactant was O2. Okay. All right, and we don't have to belabor this too much because we have brought in limiting reactants in recent units as part of problems on the test. So from stoichiometry, we covered the big ones here. I think the little ones you guys can fill in the blanks on your own. Let's talk about gases. So first and foremost, to understand gases, there was the basic properties of gases, right? And they went something like this. All gases have mass, right? So this is very easily verified by taking an empty tank and then taking a scuba tank and filling it up and weighing it. Clearly it weighs more, right? Gases are tiny particles, always in motion. Right? They're always moving. The proof that gas particles are always moving is that if you have a balloon, the balloon retains its shape. What is causing a balloon to have shape?
Gas inside.
But what is the gas inside doing?
Bouncing around.
The fact that it's colliding against the walls of the balloon, which means it has its shape, right? So gas particles collide with container walls. There's lots of space in between. And when I say gas particles, particles can be atoms or they can be molecules. If they're going to be atoms, they're going to be something like neon, helium, argon, right, etc. Or if they're molecules, that means there's things like ammonia, H2, O2. Remember the difference? A molecule is when your atoms are bonded to each other covalently. So you can fill up a balloon with either, when you fill it up with hydrogen or you fill it up with helium, molecules versus atoms. All right. Gases cause pressure. I should mention that here because that's actually, it has to do with the pressure is caused by the collisions with the container walls. So, when we talk about pressure, we spent a fair amount of time talking about pressure in the atmosphere.
It crushes down the weight of like one atmosphere pressure, right?
Yeah, depending on where you are, if you are at a high elevation or a low elevation, the amount of air pressure you feel will be different. So if you're at what we call sea level, 1 atmosphere is the amount. If you're on a mountain, there is less air above you, so gravity is not able to pull as much material downward on you, which means you feel less pressure. And if there's less air, it also makes it more difficult to get the required amount of oxygen that you need to breathe, which is why you start breathing faster, because there's less oxygen per breath at higher elevations. Okay. People climb mountains. It happens all the time.
What is that pose he's in?
He's a stick figure drawn on Notability with an Apple Pencil. You're talking about, can you even see the pose? You can't see the pose.
Yeah, he's like doing this.
Okay, all right. He's celebrating the fact that he made it on top of the mountain. Remember, there are different units. So the standard unit is 1 atmosphere, but it's also measured in millimeters of mercury. By the way, these unit conversions will all be given to you. You don't have to memorize them. We also 101.325 kilopascals, and then there's 14.7 pounds per square inch, which is an engineering unit. So there's all sorts of different units. It doesn't really matter. The point is you have to know how to convert them. In a reaction in a lab, when gases are produced, we often use what's called a manometer. A manometer is a vessel that has a tube that is filled with a dense liquid, usually mercury. And so if there's a trapped gas, the trapped gas is going to push on the mercury, but the other end is open to air. And the air is pushing down on the other end. So what's important here is the difference in height between the two sides. So let's say in this instance, the difference in height was 7.8 centimeters. And let's say that the air pressure that day was 1.05 atmospheres. What's the pressure of the trapped gas? Well, first things first, just look at the picture and decide which has more pressure, the air or the trapped gas, which is pushing harder. Yeah, the trapped gas is clearly pushing harder, so therefore you know the value for the gas must be greater than the air pressure. If all you know is the air pressure and the difference in height, then it stands to reason that you can take the air pressure and you can add the difference in height, and that will result in the pressure of the trapped gas, because the trapped gas pressure is supposed to be greater than the air pressure anyways. But in order to add, you need to make sure that they're in like units, right? So you have to convert both of these into the same unit. It doesn't matter which one, just they have to be the same. So I'm just going to take the 7.8 atmospheres, convert this into atmospheres. So what do we know about centimeters? We know that centimeter is 10 millimeters, and we know that there's 760 millimeters per atmosphere. So the difference in height is equivalent to 0.103 atmospheres. So therefore, P gas greater than P air. So the pressure of the gas is equal to 1.05 plus 0.103, so 1.18. .108. Whoops, there's an O in there. Can I not add? All right, I can't add. Glad I'm recording this. 1.153. Okay.
How do you get the previous one through?
I was able to add that apparently. All right, so moving past manometers, now we move into the simple gas laws. P1 V1 is equal to P2 V2. P1 over T1 is equal to P2 over T2. And V1 over T1 is equal to V2 over T2. So this all culminates in this, what we call the combined gas law. And just remember that in any kind of problem where conditions change, if there is a condition that is not mentioned, you are to assume that it is constant. And therefore, it drops out, and you don't plug anything in. So like if I said, I changed the pressure, what's the new volume, but I didn't mention anything about temperature, then you can safely assume the temperature has not changed. If the temperature has not changed, then you're ignoring the temperature aspect of this law. All right. Temperature, always in Kelvin. Very important. Right, always in Kelvin. Gases have to have temperatures measured on the absolute scale, meaning we can't use any negative values. So always in a gas law problem, convert your temperature into Kelvin before you do anything else. The ideal gas law is the second gas law. Pressure, volume, N is moles, R is a constant. And these gas laws will be given to you as well as the constant. Yes.
Refresh my memory, then so I can put it down. What is what is 0 C in Kelvin?
So Kelvin is Celsius plus 273. Yeah. No. So the difference between the ideal gas law and the combined gas law is that the combined gas law is focused on changing conditions, whereas the ideal gas law is focused on using the amount of gas that you have, the moles. Right? Either solving for the moles or using the number of moles to solve for whatever is being asked. So it's often that when you use the ideal gas law, you will have to use some kind of mole ratio, some kind of stoichiometry, because the particular gas in question might not be the one that you have the information about. So in other words, let's say there's this reaction A plus 2B, bless you. So these plus 2B forms 2C, right?
There's no marking below it.
Gas.
Oh.
So let's say that you have the information. Let's say you find, moles of A, but the question is asking about C. So if I gave you the temperature, the volume, and the pressure for gas A, you would use the ideal gas law to solve for the moles of A, but once you got moles A, then you would use mole ratio to solve for moles of C. Okay. And this is just another way. You guys, mole ratios have pervaded in almost every type of problem that we have done. Like it's everywhere. So that's kind of old news. Also of interest is the derived form of the ideal gas law. How if we can substitute, if N is equal to the mass, that's grams, mass divided by the molar mass, that means we can use this form of the ideal gas law, the substituted form. And this is useful because this allows us to directly find the molar mass, but we can also rearrange it further and find the density of a gas. Right? Because if you remember, density is mass over volume, which in this case would be grams over volume. So if I can rearrange this equation to give me P times mm over RT is equal to the grams divided by the volume. And this would be how we solve for density if we needed to. Whereas this would be how we solve for molar mass. Now, these are not going to be given to you. You have to get here on your own, right? By the way, I did post the formula sheet that you will be given. Like I will physically give you a formula sheet if you're here in person. If for those of you at home, the formula sheet is posted in the semester 2 review folder. It literally says semester 2 final exam formulas. So print that out and have that, handy before you start the exam. It would be a lot more efficient if you had it on paper as opposed to having to toggle back and forth. All right. The other thing with gases is during labs, we often have to collect gases. And when we collect gases, it's really hard to do that with just test tubes. So what we do is we bubble the gas through water. So we have a sink. We get an upside down bottle that we fill the bottle with water. And as the gas is made, the gas is collected. But what we realize is that there's also water vapor. So there's two different gases in here. So this is why we have to subtract if we want to get the pressure of the gas, which is ultimately the goal. This is what we really need, right? And this is given, and this is from a table, which means it's given. So the first thing you do in any kind of problem where they talk about collecting gas through water is you have to subtract out the water vapor. So P total minus pH2O is how you're going to find P gas.
we get pH2O?
You would have to be given that in the problem. Otherwise, you wouldn't be able to do it. Yeah. And once you get the P of the gas, then it's most likely a straightforward ideal gas law after that point. But you have to recognize that this must be done before you proceed. Okay. This is often called the wet gas here, right? Whereas after you subtract, this is called dry gas, and that's what you use. All right. Those are the main points from gases. Next up, we talked about solutions. So with solutions, we talked about what is a solution. Solution consists of two parts, solvent and solute. Right? The solvent is what there is more of. Solute is what is being dissolved. It's always far less solute than solvent. Well, I shouldn't say always. Most often, right? Most often you have less solute than solvent. So, we talked about terms like saturated, unsaturated, super saturated. What those mean, right? Saturated means maximum amount of solute is dissolved. Whereas if it's unsaturated, well, then you can still add more. And supersaturated is unstable, has more dissolved than is allowed. We talked about solubility curves, what they mean. Different substances have different patterns. Main idea, solids are more soluble as temperature increases, gases are less. We talked about interpretation. So if I told you, there was 20 grams, if there was 20 grams of, B, right? So let's say this is 20. And let's say this was 20 degrees. Solution B, the solubility is 20 grams of B per every 100 grams of water at 20 degrees. That means it's saturated. You then know that if I told you there was more, it would be supersaturated. If it was less, it would be unsaturated, right? So we have to interpret whether something is or is not saturated based on a solubility curve. And then, quantitatively, we calculated concentrations. Molarity. Which is the moles of the solute divided by what the total volume is in liters. Molality, moles of solute over the solvent only in kilograms. And then mass percent. Mass solute or mass of solution. Each have their own uses. Molarity is the most common measure of concentration used in any kind of chem lab. Molality is what we used for changes in temperature, because when temperatures change, the solvents expand or contract, and that changes their volume, which means the molarity is not consistent. So we don't want to use molarity at really high or really low temperatures. And mass percent is used when you have, when you're talking about pollutants, toxins, things like that, or impurities, or on an industrial environmental scale. So in chemistry, we use it, but not as much as molarity. So obviously molarity is the one we've been focusing on. All right, so applications of solutions then, or the colligative properties. Boiling points, freezing points, right? So boiling points increase when solute is present. Freezing points decrease when solutes are present. This is calculated, the change in the temperature for freezing or boiling, using this equation. The Kb value is the boiling point constant, and if the solvent is water, that is the value, and of course that is going to be given to you. You don't have to memorize that. Molality is the concentration used. I, who remembers what I is? Yeah, number of ions, right? Van 't Hoff factor, right? So you have to be careful about this, because if I could give you a simple compound, something like this, KCl, I is clearly equal to 2 because you get K plus and Cl minus, right? But you got to be careful about the tricky ones, because some people will take something like this, NaNO3, right? And so some people might say, oh, well, there's Na, there's N, and there's 3 O's. What's that? That's the constant value. So I've got, some people might think, oh, I is equal to 5 because there's 5 atoms. No, that's not correct. right? Its I is actually equal to 2 because NO3 is a polyatomic ion and it stays together, this is why you have that list, why you have the chart on the back of your periodic table, so you can refer back to it. If you think something's a polyatomic ion, you should check, because the polyatomic ions stay together. Obviously, if you don't get the correct Van Hoff factor, that means you plug the wrong number into the equation and you would get a wrong change in the boiling temperature. All right, just be careful about that. Okay, we also talked about dilution, because solutions often need to be less concentrated than what we buy them at. So I buy 18 molar sulfuric acid, but I cannot give you guys 18 molar sulfuric acid to use because you guys would burn yourselves. So I have to dilute it down with lots of water. And so we talked about how you do that. So if I have 18 molar H2SO4, and what I want is 2 liters of 0.5 molar H2SO4. How do I get that? Well, you're given 18 molar, and that's the original concentration. You want 2 liters, that is the volume that you want, and the molarity that you want is 0.5. So you're really solving here for the volume of the initial stock solution, so V1. So when we plug the numbers in, 0.5 molar, 2 liters, 18 molar. So essentially 1/18. Yes. So what we would need to do is we would need to measure out 0.0556 liters. And then how you make this matters, because when you're making a molar solution, you got to make sure you know what the total is. And so the total volume is going to be 2 liters. So you need what's called a volumetric flask that is calibrated. Right, so you put your solute, you put your solvent in here, and you just make sure that you don't go past the 2 liter mark. You don't measure the amount of water. There's no point in trying to measure how much water you need, beforehand. You just add water and keep adding water until it gets to the mark. All right. And then that brings us to equilibrium, which we just spent the last unit on. Anything I missed here that you guys want to go over? Did this kind of fast. Yes?
So if you're solving using Molarity equations P equals NIP or something, for the volume part, do you use milliliters or liters?
Good question. So to answer that question, let's just jump back to the ideal gas law. So for all of these variables, this is very specific because your volume for the gases, it must be in liters when you're using the ideal gas law. For any other gas law, it doesn't matter, but for the ideal gas law, it's the most picky. It's got to be liters. The pressure has to be atmospheres, and of course, the temperature must be in Kelvin. And if you ever forget, just look at the units in the value of R. It will tell you what units you have to have, because that's the only way that they would cancel, is if you use liters, if you use atmospheres, if you use moles, and you use Kelvin. All right. I don't think we need to review equilibrium now, since we had just gone through that. So I'm going to stop this recording. Okay, yes?
There's something about like adding 10 milliliters of water to some solution and finding concentration. I didn't know how to do that.
Okay.
Maybe I'm just dumb, but.
Okay, so let's say we have 5 milliliters of 0.05 molar NaNO3. Actually, no, I'm changing that. NaCl. Let's say we have 3 milliliters of 0.001 molar silver nitrate. And let's say we have 2 milliliters of water. So we might as well just work out this problem here since we're here. The KSP value of AgCl is, off the top of my head, I don't know, but I'm going to write a number that is about close. So I'm going to say 1 times 10 to the negative 8th. If you looked that up, I'm saying right now, disclaimer, that's probably wrong, but for the purposes of this problem, we're just going to go with it. Okay, so the question is, will we get a precipitate? Okay, so remember that I gave you the KSP for a silver chloride, and you hopefully, if you kind of remember your solubility rules, even if you didn't, you're getting the solubility rules, right? So you would realize it's silver chloride, which is of interest here. So AgCl is our solid, and here's our dissolving equation, all right? And so I need to figure out which way this is going to go. So I need to take the concentrations of silver times the concentrations of chloride and see what Q is, and then compare Q to KSP. So I need concentrations. So for the concentration of silver, it would be the moles of silver over the volume. So we need both of those things. To find moles of silver, no, not yet, because we need to figure out how many moles there are first. So 0.003 liters times 0.001 moles per liter of AgNO3 is going to be 3 times 10 to the minus 6 moles of AgNO3. First and foremost, is everyone okay with how I'm getting moles? I need to get moles of both compounds, all right? I don't care about the nitrate, and I understand that in every silver nitrate there's 1 silver. So effectively the moles of silver is still the same number. Now the question is, how do I find molarity? I have the moles, but I need a volume because I took 3 test tubes and combined them into 1. What is my total volume of my final test tube? 10 milliliters, but in liters it's going to be 0.01 liter, right? So therefore, so to find the molarity, it's 3 times 10 to the minus 6 over 0.01, which is 3 times 10 to the minus 4 molar silver. That is how you find the concentration when water is added. You have to add the water volume to the volume of the other 2 test tubes to get your total. And likewise, if I did this with the chloride, so I've got 0.005 liters times 0.05 molar. (2.5 times 10 to the minus 4 moles of NaCl. The sodium does not matter here, so it's 2.5 times 10 to the minus 4 moles of Cl divided by 0.01 liters. So it's going to be 2.5 times 10 to the minus 2 molar Cl minus. So I have my 2 molarities now, and I can Solve for Q.
Wait,
Oops.
length divided by 0.0102.
So it's an L.
Oh, it's an L. Sorry. I'm sorry.
Those darn twos. All right. So the last thing we would do is we would go ahead and substitute these in. So the value of Q then is 7.5 times 10 to the minus 8. How does Q compare to KSP, to my fictional KSP? It's greater. So will we see precipitate? Yes, we will, because when Q is greater than K, reaction goes backwards, and that backwards means solids.
Thank you.
All right.